Hello. In today's video, we're going to talk about measures of relative standings and the way we distinguish relative standing visually, and that's with a box plot. So the last few things we looked at, we're looking at how we measure kind of a whole set of data. We can find the mean, we can find the standard deviation, variance, right? Those are things that tell us things about the data set as a whole. But really what we're going to talk about today is how we can talk about where an individual piece of data falls within that set. And the way we actually measure that is by measuring the number of standard deviations away from the mean that a measurement lies. That's kind of the best way we have to measure what we call the relative standing. And so that idea is what we call a z-score. So a z-score is going to measure the distance between an observation and the mean per units of standard deviation. And we kind of get two formulas, even though they're really the exact same, right? For population, we have a mean that uses mu. In this case, for samples, the mean is x bar. And he said in the last video, the standard deviation for a population is sigma, whereas the standard deviation for sample is just s. So in actuality, these two formulas are quite the same. And it's not just enough when we talk about standing, it's not enough just to know how far away a data point is from the mean, right? We'll see in an example that that's not really going to tell us the whole story. But what we want to know is how far apart those two things are in relation to how far spread out everything is. So, if a data point is pretty far away from the mean, but everything is pretty far away from the mean, well, that doesn't really tell us anything if we don't have that context. And dividing by the standard deviation, those things really kind of give us the context of how far away things are. So if we look at this question, here we have a set of data, 1, 1, 0, 15, 2, etc. And we've calculated the mean of that to be 3.0 and the standard deviation to be 4.42. We want to find the z-score of the two different data points for 4 and the data point for 15. So for 4, if we compute the z-score, I just take x minus mu over sigma. Our data point is 4. Our mean we computed was 3.0, and our standard deviation was 4.42. And if I compute that, we get 0.2262, which standard deviation, we always round to 2 decimal places. That will come a little bit more clear in chapter 6 as to why we want to round z-scores always to 2 decimal places. So for 15, we can do the same sort of calculation, x minus mu over sigma. In this case, we'll do 15 minus 3.0 over 4.42. If we compute that and round it to 2 decimal places, we'll get 2.71. And so we can see that this data point for 15 has a large z-score. And the z-score, again, tells us kind of the relative distance between a data point and a mean measured in the units of standard deviation. And this helps tell us, in the previous section, we were looking at significant values. Well, z-score is one thing that helps tell us significant values. And that measurement was 2 standard deviations. So it turns out that a z-score between -2 and 2, which would be within 2 standard deviations of the mean, those are not significant, right? Those are usual. But a z-score that's more than 3 or more than 2, that's where we kind of think about outliers. So let's look at some important properties of standard deviations and z-scores. So z-scores, again, are expressed as numbers with 2 decimal places. The key is they have no units. They are measured in units of standard deviation, right? So they're not, this value is not 2.1 feet or 0.23 inches. It's just kind of a value in a vacuum. Data points or values are significantly low if their z-score is less than -2. So that would be like -2.5, -3, or -4, something like that. And a value is significantly high if its z-score is greater than or equal to +2. And we can see that this data point up in this example of 15 is what we would consider significantly high because its z-score is greater than 2. If a data point is less than the mean, that's when our z-score is negative, right? Again, our formula for z-score is going to be x minus the mean. In this case, we use the sample definition divided by s. If this value, if our data point is smaller than our mean, well, then when we subtract those two, we're going to end up getting a negative number, right? That's how we would get kind of a negative number. Let's do another example of this. This example, we want to figure out which two data values is more extreme relative to the data set it came from, right? This is going to demonstrate that really what we're not concerned about is how far away a data point is from the mean, but more how far away it is relative to the rest of the data, relative to the standard deviation. So in this first situation, we have a 4,000 kilogram child. The mean weight, we found to be 3,152 grams with a standard deviation of 693.4 grams. So we can just compute the z-score of that baby's birth weight of 4,000 grams minus 3,152 divided by 693.4. And if we compute that, I'm going to get 1.22. That birth weight is almost 1.25 standard deviations away from the mean. If we look at this other situation, a 99-degree temperature of an adult, when they found a sample mean of adults for the internal body temperature to be 98.2 degrees with a standard deviation of 0.62 degrees Fahrenheit. And so clearly, this is a smaller difference, right? To go from 98.2 to the value we're talking about of 99 degrees, clearly that's a smaller change, right? This is almost 900 grams, whereas this is 1.8 degrees. But again, we're not really measuring that. I'm sorry, not 1.8, but 0.8 degrees. But we're not measuring difference. We're measuring relative distance to the standard deviation. So when we compute the z-score, again, I'll take my data point of 99 minus my mean, 98.2, and divide it by my standard deviation, which is 0.62. And that division is the really important part of z-score. And if I compute it and round to 2 decimal places, I'll get a z-score of 1.29, meaning the temperature is the larger relative change, right? It's not the biggest change, right? It's the biggest relative change. That relative to its data set, it has a larger value that it increased by, right? It's almost like saying it is harder to increase the temperature than it is to increase the birth weight because there is less variation, right? That bottom, that denominator is telling us there is less variation in our set. One other value that's really important, or one other idea that's really important in a statistics class, is this idea of percentile. And what a percentile is, the p percentile is the data point x that is greater than p% of the data. If that data point is greater than p%, then it has to be less than 100 minus p% of the data. So when we hear the 50th percentile, it's the data point that is bigger than 50%. When we hear the 27th percentile, that's the data point that is greater than 27% of the data. And so how do we find the percent value? Well, that's really easy. So the process of finding the percentile. So the percentile value of x is just going to be the number of values less than x divided by the total number of values times 100%, right? Really straightforward. So what we have below is just kind of a list, percentiles. The first thing we're going to need is a sorted list of data. for percentiles. And if we have kind of a longer list like this, it will always be sorted for us. So let's say an airport Verizon cell phone data speed listed below. We arrange it in increasing order. We want to find the percentile that corresponds to a speed of 11.8 megabits per second. So what we'll do is we'll find 11.8 megabits per second. And to find this percentile, I'll want to count, well, how many data points are listed below? Are listed less than that, right? 1, 2, 3, 4. If we do this, there's 10 in each row. The percentile for 11.8, there are 20 data points less than 11.8. If we can see, there are 5 rows of 10 out of 50. I multiply that by 100%, and I get 40%. And so our final answer, we'll say it's P40. This is just the notation for the 40th percentile, or I'll write or instead. Or we can say it's the 40th percentile. Right? Either one of those would be a correct way to say that 11.8 is the 40th percentile. Another type of question we might want to ask is what data value corresponds to a given percentile? For example, what data speed is at P60 or the 60th percentile? Right? Kind of going backwards, right? I know the percentile I want to find kind of the data value, in this case, the internet speed that corresponds to the 60th percentile. And so to do that, we're going to kind of go through a little flow chart. And so we want to come up with some values first. Again, N is going to be the total number of values in our data set. K is the percentile being used. So in this case, K is going to be 60 because it's the 60th percentile. N is going to be 50 because there are 50 data points. L is the locator that gives the position of the value. And what we're really going to do in this set, right, when we have a sorted set of data, what this is really asking us to do is to find somewhere in here, maybe there, maybe here, maybe here, what data value corresponds to a given percentile. The only way we can do that is by finding the location in our data set. What value is it? Is it the second value? Is it the 36th value? You might get things like, is it the 37th and a half value? We'll have to figure out how to deal with that. The last kind of variable we want to use is what we call P sub k, and that is the kth percentile. That just corresponds to what this is. But really, these are the three that we want to know. The total number of data sets, N, K, which is the percentile being used, in this case 60, and L is going to be the location that we want. So let's look at this flow chart. We'll kind of go this step by step so it's not so overwhelming. So again, to start, we're going to sort the data. That's already done for us. The formula we're going to compute that uses those three things is this. We're going to compute L is equal to K divided by 100 times N. The location of our percentile is going to be the percentile value, so the 60th percentile in this case, divided by 100 times N. Whenever we have a division problem, there is always a chance that we might get a decimal. So what happens in this case if we get a whole number or we get a decimal? So is L a whole number? Well, there's a very easy way to deal with this. If L is a whole number, then the value of the kth percentile is going to be the mean of what L is and L plus 1. The location of those pieces of data, not the number L and L plus 1, but the data locations that correspond to L and L plus 1. What if L is not a whole number? What if we do this division and we get a fraction? What we're going to do is we're going to alter L by rounding L to the next whole number, and then the percentile value we're looking for is that value. So let's do an example. We want to refer to those data speeds again, and we want to find the 60th percentile. So our data is already sorted. We'll do L is equal to K divided by 100 times N. In this case, that's 60 divided by 100 times 50. If I compute that, I get 30. And so if we kind of look up at our flow chart, since L is a whole number, what I want to do is I want to take the 30th piece of data and the 31st piece of data. And I want to find the average of those two. And that value will be the 60th percentile, the data value that corresponds to the 60th percentile. So I'll set this up. I'm going to add two numbers and divide by 2. That's how we find the mean of two numbers. So if I go all the way back up to my data chart, I know that I have rows of 10. So this is the 10th piece of data. This is the 20th piece of data. This is the 30th piece of data. So I want 30 and 31. So I come back down here. I'll take 15.1 and 15.5, add them and divide by 2, and I'll get 15.3. And that is the 60th percentile data value. Right? We're just going to look at the chart. We're not going to do another example of this per se, because we're going to introduce another topic that deals with percentiles, and it will give us kind of more practice at this. So why are percentiles important? Percentiles help give us kind of a really important value of a percentile called a quartile. And quartile are measures of elevation, which there are 3 of them. We denote them Q1, Q2, and Q3. And they are called quartiles because they divide the data set into 4 groups with about 25% of the data values in them, right? It might sound weird at first to have something called quartiles and have only 3 of them. But the quartiles refer more to the data collection points, that if I have kind of a whole list of data and I cut them into 3 spots, well, I'm going to have 1 spot and a second spot and a third group and a fourth group. So the quartile really refers to the groups that these 3 data values cut themselves into, right? Here's a chart which kind of tells us what we're looking for, that we call Q1 the lower quartile. It's going to separate the bottom 25% of our data from the upper 75%. We have Q2, and the nice thing about Q2 is it's just the median. It's going to separate the bottom 50% from the top 50%. And Q3, we call the upper quartile. It's going to separate the top 75 or the bottom 75% from the top 25%. Right? That's what these are. And so because the first quartile is the data point that is larger than the first 25% of the data, that tells us that Q1 is actually the same as P25. And because the Q2 is the data value that is bigger than 50% of our data points, that's the same as P50. Likewise, Q3 is the same as P75. It is the data point that is larger than 75% of the data. And so we typically don't find quartiles just to find them. We find them to sketch them or to plot them. And the plot we use is a box plot. But the language of a box plot is the quartiles along with 2 different data points. And if we have 3 quartiles and 2 data points, that's going to give us what we call the 5-number summary. The 5-number summary consists of 5 data points: the minimum, Q1, the lower quartile, the median or Q2, the upper quartile, the Q3, and the maximum. And so by definition, 1/4 of the data will always lie between any 2 of these consecutive numbers. So between the minimum and the lower quartile, there's 25% of the data. between the median and the upper quartile, there's a different 25% of the data. And so the 5-number summary, if we were to sketch this out on a horizontal axis, is actually what a box plot is. And so we'll practice finding quartiles and we'll practice finding 5-number summaries. But to do all that, we're actually going to construct a box plot first. And a box plot, again, is used to describe the shape of a distribution and help detect outliers in our data. So how do we construct a box plot? I like to think of constructing a box plot as really having 3 kind of discrete steps. The first one is we have to find the 5-number summary. We have to find the minimum, Q1, Q2, Q3, and the maximum. These are all kind of computational questions. The second step is we want to construct a line segment on a horizontal axis that extends from our minimum data value to our maximum data value. And then to get its namesake, we need to somehow draw a box. We're going to draw this box a rectangle with one vertical line box at Q1, the other one at Q3, and we'll draw the box there. And inside that box, we'll draw a line at the value, oh, that's a typo, of Q2, which is the median. And so let's kind of go through all of these things, finding the 5-number summary, which we'll find the quartiles. We'll construct a box plot for this large set of airport data points. All right, so to do this, I need to find my 5-number summary. And so we'll do this kind of in 2 steps. We'll find the 5-number summary, show how we kind of represent that, and then we'll build a box plot. So 5-number summary, again, for the 5-number summary, again, we need the minimum, Q1, Q2, Q3, and the max. These 2, the max and the min, are going to be the easiest to find in a sorted set of data. Right? So if I have a big list of data, I might circle my data points if I have them. To find Q1, right, we said that's the same thing as finding the 25th percentile. Again, to find the 25th percentile, I have to use this formula that we had of the location of that percentile value is k divided by 100 times n. In this case, this is 25 divided by 100 times 50, which is 12.5. Do we remember what to do if our data point, if our location data is a decimal? Remember, if our data point is not a whole number, right? It's not a whole number. We're going to change the value of L by rounding it up to the next whole number. And the value of my percentile is that Lth value, counting from kind of the lowest number of our sorted piece of data. So because we get an L value of 12.5, I round that up to 13. And so our 25th percentile is going to be the 13th piece of data. So again, I have rows of 10, so that's 10, 12, 13. That is going to be Q1. So let me actually write these down here so I don't get confused. Q1 is 7.9. Our max we said was 77.8. Q2 is the median or the 50th percentile. I'm going to compute this by using percentiles. Just instead of finding the median, right, we'll just do percentiles because we're kind of in percentiles mode. So I'll do 50 divided by 100 times 50, right? I'm looking at the 50th percentile, but there's 50 pieces of data. It's okay if those are repeated. That's more of just a coincidence. And if I do this, I'll get 25. And again, if we get a whole number, right? I'll write that. That's the 20th piece of data. I'm not going to scroll back, but we look at the 25th. This says I look at the 25th piece of data and the 26th piece of data and find their mean or find their average. So this is 20, so 21, 22, 23, 24, 25, and 26. So that's going to be 13.7 plus 14.1 divided by 2. If I get that, I get 13.9. So that is Q2, 13.9. And to find Q3, I go to find P75. So to do that, I have to do this location formula again. I'm looking at the 75th percentile divided by 100 times the 50 pieces of data we get. And if I do that, I'll get, let's see, 37.5, which again, this is not a whole number. So we round up to not 38. This is going to be the 40th piece of data down here. So that makes this 29. And that makes this the 38th piece of data. So Q3 is 21.5. And so when we find all this, really the best thing to do is for the 5-number summary is to kind of write this so it's a little bit easier to read. So we could put it in parentheses or just list them. 0.8, 7.9, 13.9, 21.5, and 77.8. Those are my numbers that correspond to my 5-number summary. Now, let's talk about how to turn that into our box plot. To do that, we'll draw a horizontal axis starting from 0. And because our top number is in the high 70s, I'll put this up to 80. And so I want to plot, right? And I'll kind of put a scale. So halfway in between, that's 40. That's about where 60 is. This is about where 20 is. 10. Then that's about 30, 50, 70. So I want to put a little horizontal line where my minimum thing is. That's going to be about as close to 0 as I can get. And I want to put another kind of little dash, excuse me, where the 77.8 is. So that's going to be more or less there. And again, I'm not looking for exact. I'm looking for like in the ballpark, right? So if this was 77.8, yeah, I believe that's about where 77.8 is, right? If you put that dash right around here, of course, that's going to be wrong. We're going to have a line connecting them, just like that. Then what we're going to do is we're going to take, so we got our min and our max, we're going to take our Q1, so let me just label them again. Q1, Q2, Q3, and our max. I'm going to put a slightly larger vertical line at right around where Q1 is, and we'll label it Q1. And then I'll put another vertical line of about the same length right where Q3 is. And then I'll put a box there. And then right where Q2 is, 13.9. So that's going to be close to 15. So about there, I'll put Q2. This is our box plot. And what this does, again, the idea of the box plot is to break this thing up, is to break the spread of our data up, not into 4 equally length areas, because clearly between Q3 and our max is the longest piece of data in terms of an interval length. But what it does is it tells us how our data is distributed, right? This kind of long interval only contains 25% of our data points. This small interval between Q1 and Q2 also contains only 25% of our data. So we would describe kind of this little space as being much more densely populated. There's the exact same amount of people or same amount of data points in this kind of long interval as there is in this kind of smaller squarish area, right? Same amount of data points, but it's just spread out much more over here than it is over here. And so again, this 5-number summary, although we lose some of the precision, we only have 5 data points. we get some nice presentation. It tells us exactly kind of how spread our data value is. All right. If we have any questions, feel free to contact me. I'll be able to help you go through everything. If not, have a good rest of your day, and I'll talk to you next time.